on the topic of distillation. Hopefully you can see my PowerPoint presentation. So when we speak of the distillation, initially we only have one process stream. But from this particular process stream, we have the formation of the vapor, which actually flows already countercurrent to the liquid stream, or we call it the vapor phase flowing countercurrent to the liquid phase, and the two being intimately contacted.
Miss, excuse me.
Yes. Yes.
Wala naka-share ang slide.
Wala naka-share. Wait, ha. Did you see it already?
Miss. Yes, miss.
Okay. Okay, so as I've been saying, so distillation initially has only one process stream. But from that particular single process stream, we produce the vapor phase. And that particular vapor phase is the one that flows countercurrent to the liquid phase. As a result, the two phases are intimately contacted. So distillation primarily utilizes this vapor and liquid phases at essentially the same temperature and pressure for the two coexisting zones, or for the two coexisting phases. So the two coexisting zones that is being referred to in here is the top part of the column and the lower part of the column, which you will know the names later on. These two phases, referring to the vapor and liquid phases, are coexisting in these zones of our distilling column. So our distilling column may use either random or structured packings. So these are packing materials responsible to intimately contact the liquid and the vapor phases. Now, other columns may utilize plates or trays to bring the two phases into intimate contact. Now, our column, our distilling column, otherwise known as the still, may be operated continuously or in batch mode. Now, depending on the number of factors. So we can operate it continuously. Most of the time, it is operated continuously or in batch. So as to which of the two modes will be used, that depends on the scale, the flexibility of operation, and the solid content of the feed. Now, all components in our original feed that is processed by our column are present in both the phases that are being contacted. That is the liquid and the vapor phases. And the vapor phase is created from the liquid phase by the process of vaporization. So as I have mentioned, initially we don't have the vapor phases. We only have the feed. But from that feed, we produce both the vapor and the liquid phases. Now we carry on. So the feed material for distillation is to be separated into fractions. So in the case of crude oil, so the reason why it's called crude oil, because in its crude form, it cannot be still used further in different industries. So what distillation does, it separates this particular processed or refined crude oil into fractions. So depending on the refinement that is needed. So it is separated into fractions and is introduced at one or more points along the column shell. Now, speaking of introducing this particular feed into your column, either in one particular part of your column, most of the time it's in the bottom part that we are introducing the feed, but there are other columns that has what we call intermediate streams. Now, nonetheless, our focus in this subject, in this course, is just for a distilling column that processes only a single feed. Okay? Now, for the distilling column, the liquid phase runs down the column. So it's the one that is flowing downward, cascading from tray to tray or from stage to stage, whichever is applicable. So we refer to trays if our column is using trays. We refer to stages if our columns are using packing material. So the liquid cascades from tray to tray while vapor flows up the column, contacting the liquid in each of the tray. So they flow countercurrent to each other, the vapor coming from the bottom part of the column. Now, the liquid reaching the bottom of the column is partly vaporized in the heated reboiler to provide the boil up, which is sent back or sent up the columns or sent back up the column. So this is the reason why that from a single feed stream, we produce the vapor. Because as the vapor goes down the column initially, it's being collected at the bottom part. And the reboiler or the auxiliary equipment at the bottom part of the column is responsible to turn part of this liquid into vapor. So part only. So that is the reason why we have the vapor flowing now countercurrent to the liquid that goes down. So the vapor goes up, flowing against this liquid that goes down. So the purpose of this auxiliary equipment, the reboiler, is to provide the boil up vapor. So initially we don't have the vapor. It's this reboiler that produces that. So the remainder of the bottom liquid, so I said it's only partly vaporized. So part is vapor, still the other parts of this collected liquid at the bottom of your column is withdrawn as the bottoms or the bottom product. So the main product of distillation actually in most processes is the distillate. But in some processes, the bottoms product are also being used further or being processed further. And as such, they are also referred to as the product because they are also further processed to produce other materials from it. Okay, so the liquid that is not being turned into vapor or that was not turned into vapor is called the bottoms liquid. It's really collected as the bottoms liquid or bottom product. The vapor, on the other hand, reaching up the top of the column is being cooled. So the vapor, remember, part of the liquid was turned into vapor by your reboiler. So that vapor, as it reaches the top of the column, is being condensed. So vapor reaching the top of the column is being cooled and condensed to liquid in the overhead condenser. So your distilling column now, having mentioned it, has two auxiliary equipments. At the bottom, we have the reboiler, and at the top, we have the condenser. So part of the liquid is returned to the column as reflux to provide liquid overflow. Later, when I show to you the illustration, the simplest illustration of the distilling column, we have what we call as the reflux liquid. It is part of the vapor that has been turned into liquid by your condenser that is returned back into the column to provide what we call as the liquid overflow. But the primary purpose of the reflux liquid is really to increase the purity of the final product, which is the distillate. So it's not that specified always in the discussion when you read books, but when you read in detail, especially in McCabe, you'll be able to read it there that the purpose of this reflux liquid is to increase the purity of the distillate. Now, part of the liquid, as referred already, is the reflux to provide the liquid overflow. The remainder of the overhead stream, which is withdrawn as distillate, is the overhead product. So if in the bottoms, we have the bottom liquid, in the condenser, we have the distillate. It's the final product that is being withdrawn. The part of that condensed vapor is returned into the column as reflux. The rest is withdrawn as your final product. Okay, so your column will have two now products, the distillate and the bottoms liquid. You only have one stream that was processed, and that's the feed. Now, the lighter boiling point temperatures or the lower boiling temperature components tend to concentrate in the vapor phase, while the heavier or those that have high boiling point temperatures concentrate in the liquid phase. So meaning, class, those components in your original feed that have low boiling point tend to go with the vapor and leaves as distillate in your condenser. Now, those that are heavier or those that are referred to as having high boiling points are the ones that are withdrawn in your bottoms liquid. Now, the composition of the vapor, you take note of this, this is very important. The composition of the vapor in equilibrium with the liquid at the boiling point of the liquid should be different from that of the liquid. Take the composition of the vapor that is in equilibrium with the liquid at the boiling point of that same liquid should be different than that of the liquid. Now, the vapor phase becomes richer in light components as it passes up the column, and the liquid phase becomes richer in heavier components as it cascades downward. So this is in relation to the first bullet that we have in here. So the vapor becomes rich, so meaning most of its components are the lighter components of your original feed. The heavier components goes with your liquid that goes down the column. Overall separation for distillation is achieved between the distillate and the bottom's liquid, but it depends on the following factors. So number one, the relative volatility of the components. So the degree of separation is still dependent on the relative volatility or the volatilities of the components of your original feed in reference to another. Now, it's also depending on the number of contacting trays in the column section. So, or the contacting stages in your column section. So, the column section will be discussed in the next bullet. And the ratio of the liquid phase flow rate to the vapor phase flow rate in each section. So, three factors determine the degree of separation of your distillate and the bottom's liquid. The number of trays or the number of stages of each of the sections of your column, the relative volatilities of the component of your feed, and the ratio of the liquid to vapor phases, or the ratio of specifically the flow rate of the liquid and the vapor phases in each of the section of the column. And speaking of the sections of your column, our distilling column is divided into two sections. We have the rectifying section or the enriching section, and we have the stripping section. The upper section is the rectifying or the enriching section, whereas the bottom is what we call as the stripping section. You will know it later when we'll have the graphical representation of our distilling column when we determine the number of stages, and correspondingly we're able to determine how tall our column would be. Now, our analysis of distillation, especially how we answer problems in relation to distillation, will require this equilibrium diagram. So at the start of our lesson, our first meeting, I think second meeting, we have sorry, class, I think I got disconnected. Which part was I disconnected?
So may diagram.
Diagram, okay. Okay, going back to the diagram. So this is the diagram that we are utilizing when we are using the graphical technique of determining the number of stages in our column, both in our enriching section and in our stripping section. But I would like also as well to emphasize that when we determine the number of stages, we use the shall I say, the numerical technique, and that is we don't rely to the graphical process. But nonetheless, I don't want also not to discuss this graphical process because it gives you more as I got disconnected again. Wait. I'll share my screen again. So this is the equilibrium diagram that we will be utilizing when we construct the different sections of our column, where we're going to determine separately the number of stages in each of the sections. As I have mentioned, however, we will still focus more on the analytical process of determining the number of stages, and it would be at the latter part of our discussion on this topic. Now, in this particular equilibrium diagram, you have on the horizontal axis the mole fraction of benzene in the liquid phase, and on the vertical axis, you have the mole fraction of benzene in the vapor phase. If from a particular table, if you can still recall the table that has this relationship between XA and YA, if you will construct it, you will have this particular curve for the system benzene and toluene. And by the way, this system benzene and toluene is an ideal system. Now, the 45-degree line is just written there because that's where primarily our construction lines for the enriching and the stripping section, including our feed line, is going to start. We start drawing these three lines from here. But the original equilibrium diagram would only be this curve that you see. Now, it's written also in here that the greater the distance between the equilibrium curve that you are seeing here and this 45-degree line, the greater the composition difference between the vapor and the liquid. The greater the composition difference between the vapor and the liquid, the easier it is for us to separate the components present in our feed. It says here, the greater the ease in separation. So the farther is this curve for a particular system is from the 45-degree line, the easier would be for us to separate the components of our original feed. Now, having to connect relative volatility to distillation. So actually, relative volatility is the numerical measure of the degree of separation of our components, and it's represented by alpha. So separation would only be possible if this alpha value, if computed, would be greater than 1. So the relative volatility of A with respect to B, as it is written here. Now, if I change the manner in which I write the subscript, it would be, let's say, if it's BA, so it would be read as relative volatility of B with respect to A. But in this case, relative volatility of A with respect to B. So we can determine this relative volatility based on the mole fractions of A, where A is the most volatile of all components present in your feed. So that's our A. In this case, that's our benzene. In our case here, by the way, we'll only be limiting our discussions, our analysis, our problems to 2-component systems. We will not have multiple component systems because they're very complex already. So in the case of benzene and toluene, it's always that of benzene, the mole fraction of benzene that we are using because it's the more volatile of the two, benzene and toluene. So you can use the mole fraction of benzene in the vapor phase, and that's YA, and you can use the mole fraction of benzene in the liquid phase, that is XA. Using this XA and YA, you'll be able to determine the relative volatility of this system, benzene and toluene. Or if you don't have X and Y, we can use the pure vapor pressure of the two. So PA naught and PB naught is representing the pure vapor pressure of benzene and toluene respectively. So we can use these two to determine as well our relative volatility. Now, alpha generally varies with concentration, but for binary mixtures obeying Raoult's law, meaning they are ideal mixture, the variation is negligible over large concentration ranges at constant pressure. So this variation of alpha with concentration is negligible when we are considering or we're simply dealing with binary mixtures that are said to be ideal. So not just binary mixtures, but mixtures that are ideal. Now you can read more on this concept of relative volatility in your handbook in section 13-7 and also section 13-17. So if you have your handbook already, whether hard copy or soft copy, please check on it. Now there are two methods of distillation. So method 1 here is a case wherein your vapor is produced by boiling the liquid mixture in a single stage. recovering and condensing the vapors with no liquid allowed to return to the single stage still to come into contact with the rising vapors. Method 1 does not have any reflux liquid. So all of the vapors that are condensed are withdrawn, 100% withdrawn from the top of the column. This method 1 is oftentimes only used for single stage processes. But in multi-stage processes, in the case of fractionation, we fractionate, we retrieve products from particular stages in our column. We have what we call as the reflux liquid, and that's our method 2. So the process is basically the same as method 1. You boil the liquid and then the vapor you condense. However, part of the liquid that was condensed is returned into the column or the still. And it comes into contact in countercurrent fashion with the rising vapors through the series of trays. Now, method 2 is referred to as fractional distillation or distillation with reflux. So, fractional distillation, distillation with reflux, or rectification, or fractionation are all the same thing belonging to method 2. So, method 1 is very simple. However, we expect that the quality of our distillate will not be as good as the one that we have in method 2 because primarily the reflux liquid is for the improvement of the purity of the distillate. Now, under method 1, there are 3 types. So we have equilibrium or flash distillation, which you can read further in section 13-5, 13-6, and 13-15 of your handbook. Now in here, your liquid mixture is partially vaporized. So not all is turned into vapor. The vapor is allowed to come to equilibrium with the liquid. Then vapor and liquid phases are separated. Now this can be done either continuous or by batch. So this is equilibrium or flash distillation, partial vaporization of the liquid mixture. This liquid mixture, by the way, is your feed. Now we go to the batch or differential distillation. In here, your liquid is boiled slowly and the vapors are withdrawn rapidly as they form to a condenser, resulting to a vapor that is richest in the more volatile component A, which we refer to as the first portion. As vaporization proceeds, your vaporized product becomes leaner in A. So meaning, as the vaporization process proceeds, there is less and less A that is present in our vapor already. The phrase to remember here for batch or differential distillation is the boiling of the feed, which is a slow process. Slowly boiling the feed and removing right away the vapors that are condensed. And that way, in the first part that was withdrawn already is richest in the most volatile component. Now, the third type is the steam distillation. Now, we do this in the laboratory actually. But in the industry, as the term steam, so steam here is used to separate components of a high boiling liquid solution. The purpose of using steam here is to lower down the boiling temperature of the high boiling component or components. The vapors here are condensed and the two immiscible liquid phases separated. The process of steam distillation is very costly if it's used in the industry because though it enables us to separate high boiling components of a mixture from those that are not, but it's requiring steam. So then it's a highly intensive process in terms of the use of energy. So that's under method 1. The 3 type under method 1. So this is your equilibrium flash distillation. This is an equivalent illustration in John Copley's. It's only illustrated in the form of a box. So flash distillation is the process by which a portion of the mixture is vaporized and then the vapor and liquid phases are being separated. So that's equilibrium or flash distillation, the first part in here. Okay. Now, the next one is still talking about flash distillation. So, flash distillation is the simplest method of separation. A feed stream is flushed into a chamber or flush drum, and then the liquid and vapor are allowed to separate under equilibrium. Okay, you have this separator in here between your bottom's liquid and your vapor that goes to your condenser to be turned into liquid. Now, the more volatile component here will be concentrated in the vapor stream, the less volatile in the liquid stream. Now, in this flushing process, it is flushed by throttling the feed stream to a nozzle or valve into the chamber. The pressure drops through the valve. So I think you have already encountered this process of throttling in one of your unit operation subjects. I think, if I'm not mistaken, in your transport phenomena. So you could see here a throttling device, a pressure reducing valve, a throttling device prior to your mixture of vapor and liquid being separated here in your flush drum or in your still, your flush distillation tower or column. But before that, you have this particular throttling device, a pressure reducing valve, as mentioned in here. Okay. Now the system is very close to a single equilibrium stage. What does this mean? If you will liken this system to a multi-stage distilling column, in the case of a rectifying column, it's like you only have a single stage. You don't have several stages. You don't have to think of sections in your column, just one particular stage. Why? Because you simply have it separated here. Referring to the vapor and the liquid, you just simply separated them in here and that's it. So that's just like equivalent to a single stage. Separation in here is usually not very high, and since because we consider it only as a single equilibrium stage. The term here, equilibrium, is not just something that is placed there just to make the equilibrium idea or concept applicable. Equilibrium in the sense that the vapor and the liquid phases that have been separated are said to be in equilibrium. That is why it's referred to in here as a single equilibrium stage. Now, flash distillation problems can be solved using 3 sets of equations, though we don't discuss it in detail here because if that is the case, we will be needing probably the entire of midterm just for distillation only. Just to give you an idea, why it's so complex and challenging is because aside from the mass balance, which we employ in distillation, you will also use energy balance. Later on, I don't want to discuss it in here. Later on, you will know that we don't do energy balance in distillation unless we would like to use the method we call the Ponchon-Savaret method. If we're using the McCabe-Thiele method, we don't use the energy balance anymore. We have assumptions that will simplify our computations, but will give us results comparable to that as if we're doing also energy balance. But previously, in undergraduate studies, energy balance is also being done, especially for multi-component system. In the case of flash distillation, it's a no-no just to make use only of mass balance. It has to be mass balance with energy balance plus the equilibrium relationship. That will be provided by the equilibrium diagram. So in here, you could see for an adiabatic process, in the case of our flash distilling tower, you have this particular energy balance equation that is being used. But we will not be discussing it in here anymore because, I will emphasize this, we normally in distillation only use overall material balance and component balance. So in terms of overall material balance, we only account, as you could see in here, if it's possible, I can show this bigger. Let me know if you can see it bigger. If you just do overall material balance, you will have only a single stream equated to the sum of the 2 living streams, the vapor and the liquid phases, in the case of your flash distillation. If you do component balance, then you simply use the mole fraction or the mass fractions of your, in this case, it's mole fraction that we're using, by the way. I can say it's mass also. the mole fraction of the components in your feed that you would like to use for component balance. Let's say mole fraction of A. So Z is the mole fraction of A in the feed. Y is the mole fraction of A in the vapor phase. And X is the mole fraction of A in the liquid phase. So your component balance actually is just patterned after your overall material balance. What you do with the phases that appears or the streams that appears in your overall balance equation is you just simply multiply them with the mole fractions of the component that you would like to use as a balancing identity for your component balance. Oftentimes, we use the more volatile component. So in the case of benzene and toluene, we account for the presence of benzene in the feed and we equate it to the sum of the presence of benzene and toluene in the vapor and in the liquid phases. As you can see here, the K values could also be used in terms of this equilibrium relationship that is needed as well when we do solve problems concerning flash distillation. And you have here Y equal to Kx. Now, this is your material balance, overall and component balance. This is your equilibrium equation, and this is your energy balance. So as you could see, if we are required to do all these three for flash distillation, the thing that makes it complicated is the energy balance equation. Even in the other problems concerning distillation, particularly in fractionation, the thing that makes it an extra challenge is the energy balance, which can only be encountered if we're using the Ponchon-Savaret method. But again, I'd like to emphasize we're not using it. We'll only be using McCabe-Thiele method. Okay? Now, I'd like to skip here. That way you can see the next. Now, differential distillation. That's the second type in here for method 1. So differential distillation, this is a batch in a single stage distillation that starts with the still pot, initially full, heated at a constant rate. So in this process, the vapor form on the boiling liquid, and the vapor is formed and the boiling liquid removed at once from the system. Now, since this vapor is richer in the more volatile component than the liquid, it follows that the liquid remaining becomes steadily weaker in this component or leaner in that component, with the result that the composition of the product progressively becomes weaker as well in the more volatile components. That is, the impurities starts to dominate in your product because it becomes now leaner and leaner in the volatile component. The special distinction of differential distillation is that the vapor form over a short period is in equilibrium with the liquid. The total vapor form is not in equilibrium with the residual liquid. Now, let us distinguish between the vapor that is formed over a short period is in equilibrium with the liquid. The vapor form is not in equilibrium with the residual liquid. Now, what do we mean by this? The total vapor form is not in equilibrium with the residual liquid. Anybody who can tell me what's your understanding of this? The total vapor form is not in equilibrium with the residual liquid, but rather it is in equilibrium with the liquid. What do we mean by that? What liquid and what vapor are we talking about in here? Anybody who has an idea? Again, this particular topic will not be covered in detail here. Why? Because you can see here a note. Differential distillation employs graphical integration in order to solve a problem. If you can recall graphical integration in your calculus, that's where your trapezoidal rule, your Simpson's rule apply. So that would be extra difficult because you're going to do graphical technique. As much as possible, we want things solved analytically. Because if you're going to answer a problem later in your licensure exam, you will do it anyway analytically. So, but for you to have an idea, and I'd like also to know if you understand this particular statement in here, what do we mean by this? there has to be a distinction of differential distillation is that the vapor form over a short period is in equilibrium with the liquid. So what liquid is it referring to and what vapor is it referring to? And it's not actually the total vapor form and the residual liquid that has the equilibrium, but rather the first two that I have mentioned. What do we mean by this? Anybody here who can tell us, who can share to the class his or her understanding of that particular statement? Anybody? I'd like to hear Johan. What's your understanding of that, Johan?
Yes.
Yes.
Wait lang yun. Yes.
The vapor formed, so never mind the previous phrases. The vapor formed over a short period is in equilibrium with the liquid. What liquid is it referring to? But the total vapor formed is not in equilibrium with the residual liquid. I think with the term residual, you would know what it is contrasting. So what do you think is it trying to tell you? If you're going to simplify the statement, what is it it's trying to tell you? Diin ang equilibrium naga-exist. Diin ni siya nga vapor kag liquid. Ano ni nga vapor? What vapor and liquid phases is it referring to? In contrast to the saying, it's not actually the other way around, that the total vapor form is in equilibrium with the residual liquid. What's your understanding of this, Johan?
I think, Miss, sa last part, ang meaning sang ano Miss, sang phrase, sa last part sa differential distillation, there's no equilibrium na Miss.
Wala na equilibrium.
Yes, Miss.
Okay, I'd like to hear from somebody. What about John Patrick Tagle? What's your understanding of this, Patrick?
Since wait, Miss, ha?
It's okay.
Case kay ang sa ano sa Miss na ang sa may ano lang naway ni sa labot yung Miss ang ano na ang image.
Pwede mo magamit ng image, pero you don't need the image actually. You just zero in on the term, the total vapor form is not in equilibrium with the residual liquid. Anong na-refer niya? It's not in equilibrium with the residual liquid, but rather at any particular time in the process of differential distillation, the vapor is in equilibrium with the liquid.
Kaya hindi lang siya Miss gagamit sa material balance, gagamit man siya sa energy balance.
So ano ni siyang namin sini? Actually, it has nothing to do with the energy balance. Kaya actually, sa tanan nga distilling process nga aton istoryahan, mas accurate ang aton results if we do energy balance. The problem with energy balance, class, it's a process of trial and error. And it's a process that if you have time, if you can check with John Kuplis or McCabe, it's a process that will take you around 3 pages of your book, the least 2 pages of your book, just to read and understand the entire process of using enthalpies to account for the energies that are present in all the streams that you are using when you do energy balance. So it's very complicated. Aside from that, it's trial and error, just like in, if you recall, just like in the process of evaporation. Okay? So it's complicated. Doesn't mean that in the other distilling process, hindi ka kagamit energy balance. If you do energy balance, your results would even be more accurate. However, to simplify things, we are using McCabe-Thiel, and even when I was a student, my teacher would focus more on McCabe-Thiel because it's simpler. But even if we say it's simpler, it's not even simple. So how much more if we will incorporate with it energy balance? It made things a lot difficult. Now, so we go back to the question. The vapor, the total vapor form is not in equilibrium with the residual liquid. We mean by this, the residual liquid is the liquid that remains here in your flask. Ano ba lang ginanamin sa residual? Nabilin. So the vapor that have been collected here in your condenser, that is being collected here in your distillate collector, is not, the total vapor is not in equilibrium with the residual liquid. Now, I'd like to go back to what Johan mentioned a while ago, saying that in the process of distillation at the final part, there is no equilibrium anymore. I'd like to correct that one because in all the stages of distillation, the two phases, the liquid and the vapor phases, will never separate until and when they are equilibrated. So it's always anchored on the concept of equilibrium. The phases that leaves a particular stage, or if it's only a single stage process, the phases, in this case, you only have two, the liquid and the vapor phases, will always be at all times equilibrated before they can separate. We are not concerned with the phases that enter a particular stage because they are the phases that needs to be processed pa. So they need to be processed pa. They need to intimately contact each other and separate the components that need to be separated. But the phases that leaving a stage or stages, if you have multiple stages, are always in equilibrium, or they are always in equilibrium with each other. So ang ginanamin dire nga ang total vapor collected and the residual liquid are not in equilibrium is this liquid that remains here. Because remember, in the lab, when you do this, you have this particular flask. You keep on boiling it, and then the vapor goes up here. It passes through the condenser, and then the liquid is being collected on the other side. Now, this collected liquid here will never be in equilibrium with the residual liquid. All the more, the vapor that leaves this particular, shall I say, flask, that goes into the condenser to be condensed into liquid will never be in equilibrium with the residual liquid. Hindi na siya in equilibrium with the residual liquid. So then, may question naman, ano na din ginanamin niya? The vapor form over a short period is in equilibrium with the liquid. Sa diin siya gali nga liquid in equilibrium? If I'm going to ask you, kung hindi siya ang vapor in equilibrium with the residual liquid, diin siya ga equilibrium ang vapor nga nagakadto sa condenser to be turned into liquid. Diin siya nga liquid in equilibrium, if I may ask you. Vapor at any particular time, which is condensed into liquid, where is it in equilibrium then if it's not in equilibrium with the residual liquid? So sa diin siya gali in equilibrium ang sa collected na miss. Very good. Sa collected na siya. So I will say your vapor that leaves this particular flask that is turned into liquid is in equilibrium with the liquid that it became. So the vapor that went up here is in equilibrium with the liquid that you have been collecting in here, not with the residual liquid. So that's the answer that I'm trying to ask from you. So the residual liquid is this liquid remaining in your still. Actually, amoni ang inyo still, amoni ang inyo condenser. Kung sa column na siya, amoni inyo stilo, amoni inyo distilling column, amoni siya ang inyo nga condenser and auxiliary equipment. Okay, so that's for your differential distillation. So my time here is already 6:31. We will continue this next week. So we'll have our lecture 5:30 to 6:30 also next week. I will just inform you if there's a need for me to hold classes during dry lab, knowing that you can still process anything in the dry lab if I haven't covered the necessary topics that you need in processing the problems that I'm giving you. So far, you already processed the problem set that was already placed in your Canvas for, I think, module 1. Okay, or you have answered already the questions there that are placed. But as to problems, you won't be processing any problems for now because I haven't given you yet much input or concepts that you can use or principles that you can use. So I will just inform you as we go along. So we'll meet again on Tuesday next week, the same time, 5:30 to 6:30. Do you have any questions? I'll stop sharing for now.